uh, just go over the questions on the no temp changer that you hadn't answered. So looking here at assignment sheet 1, I see really you didn't answer any of these. I'm not sure if it's because you didn't really understand them or didn't have time, but okay, the first question asks you to explain two things, to the turns ratio and mutual induction. And to talk about those, I'll just go back to the page in the unit that talks about those two things. Now, in this circuit here, this is the magnetic field from one coil induces voltage in another nearby coil by mutual induction. And by mutual induction, um, we mean that, okay, we've got, say, a transformer here with a primary and a secondary. And we've got a voltage source with a voltage applied, and when the voltage is applied, an AC voltage, you get a changing magnetic field here. It's going to expand and contract, and when it does, it's the magnetic field set up by this primary coil is going to cut the secondary coils, and when it does that, it's going to induce a voltage in it. So that's really what mutual induction means, is the magnetic field from one coil induces voltage in another coil. Okay, question 1 also asks you about the turns ratio. And in a transformer, the voltage transformation really is dependent on the turns ratio. If you've got, in this particular example, we've got 100 turns in the primary of this transformer, we've got 10 turns in the secondary. That means this thing is going to step the voltage down. And the way it does that is, I always like to think about in a transformer, the volts per turn. Okay, so we've got 200 or 100 turns in this primary coil, and say we make a circuit here, we apply a voltage, and we apply a voltage of 200 volts. Okay, so if we apply 200 volts to this thing, that means if there's 100 turns and 200 volts, then the volts per turn is going to be equal to 200 volts over 100 turns. So that's going to be 2 volts per turn. Okay, when this thing sets up a magnetic field and cuts these turns into secondary, what it's going to do is induce a voltage in the secondary on each turn that's the same as the primary. So in the secondary, in the primary we have 2 volts per turn, and in the secondary we're going to have the same thing, 2 volts per turn. But in the secondary we've got 10 turns. So we can find out what the voltage in the secondary is by just multiplying volts per turn times turns. And that's going to be 2 volts per turn times 10 turns. And that's going to be 20 volts. Okay, this thing says that this is a step-down transformer and the ratio is 10 to 1. So that means the voltage in the secondary is going to be 10 times smaller, or 1/10 of what it was in the primary. So if you have 200 volts over 10, that's 20. And that's what we came up with here, was 20 volts. Now the turns ratio in this thing, we talk about turns ratio in the unit. The primary voltage to the secondary voltage is the same as the number of turns in the primary divided by the number of secondary turns, In this primary, we've got 100 turns. In the secondary, we have 10 turns. So that means the ratio is 10, or it's a 10 to 1 step down transformer, because there's less turns in the secondary than there is in the primary. Okay, let's go back to see what question 2 is. Give the formulas expressing the relationship for the following variables of the transformer. Voltage to the number of turns. Well, we just talked about that up here, and when we talked about this transformer right here, the turns ratio is the number of primary turns over the number of secondary turns. And that ratio is the same as the voltage. So they should be across from each other. This is a direct proportion. If the number of turns goes down, say here, then this voltage is going to go down. Okay, next it asks about voltage to current. Well, let me just go ahead and write this. So primary to the secondary voltage is the same as the number of turns in the primary to the number of turns in the secondary. Now, the voltage to current is going to be different than this one. Voltage to current is an inverse proportion. The higher the voltage, the lower the current on a transformer. The lower the voltage, the higher the current. And you can see that with your step up and step down transformers you see out in the field. On the high side, you'll have a large bushing and a small wire goes to that bushing. That's because it doesn't take a lot of current to transmit a certain amount of power on the high voltage side. And then if you look at the low voltage side, they're going to be heavier bushings and they're going to be larger wires coming off of that secondary bushing if it's a step down transformer, say 12240 secondary on a transformer. You're going to have heavy wire or cable coming off of that transformer because the current's going to be large. So at any rate, if we take the number of primary turns to the number of secondary turns, that's going to be equal to the secondary current over the primary current. So see up here is E primary is to N primary over E secondary to N secondary. Here it's flipped around. The primary is equal to the secondary current and the secondary is equal to the primary. So if you know like 3 of these values, so you can plug them in and you want to find out what the primary current is, you can cross multiply and divide this out like a normal proportion. Okay, current to the number of turns. It's going to be the same thing. Let me just go ahead and go primary current to secondary current. Okay, so you know that if the primary voltage is high, the secondary turns are going to be high. Well, how am I going to explain that? Well, at any rate, it's an inverse proportion, just the way it is up here on the current. So if you draw the turns over here it's going to be flipped over. So it's not a direct proportion, it's an inverse proportion. And if it's an inverse proportion, if the primary is in the numerator on this side, it'll be in the denominator on the other side. If it's in the secondary is in the denominator here, it'll be in the numerator on the other side of the equation. Okay, so I see you've got a couple of these done on assignment sheet 2. Primary voltage of a distribution transformer is 2400 volts. The primary current's 5 amps and the secondary current's 100 amps. What's the secondary voltage? Okay, so let's go ahead and thinking about these formulas or ratios that we drew up here. We've got, we know the voltage and the current. So what we need is voltage and current. Now we know the voltage and the current are in inverse proportion. So the primary voltage over the secondary voltage is going to be equal to the secondary current over the primary. Okay, so now that we have that, and it's an inverse proportion, like I said, if the voltage goes up, the current goes down, and vice versa. So these two sides of the equal sign are going to be flipped then, primary to secondary, secondary to primary. So let's see, we know the primary voltage is 2400 volts, so let's plug this stuff in. 2400. We want to know the secondary voltage, so let's just write E secondary. And we're going to go ahead and say, okay, the primary current is 5. And the secondary current is 100. So now all we need to do is cross multiply and solve this out then. So we'll multiply 100 times ES. And that equals 2400 times 5. So now let's solve for ES. ES, if I divide both sides by 100, that means we have 2400 times 5 divided by 100. See, dividing both sides by 100 makes this one go away. So let's go ahead and divide out this 2400. Then this is actually going to be 2 zeros over times 5. And that's going to be 96. So come on. There we go. So that means that the secondary voltage is equal to 96 volts. Okay, and it looks like you've got these all under control here. Really all you need to do is go ahead and find out what this percentage is, and it looks like you've got that right. So if you take the circuit voltage, it's 2400 over the coil voltage times 100 equals 100%. So that's a tap setting of 1. Okay, I guess that wraps this one up. So I'll go ahead and take a look at regulators now.